Hi, welcome back to Chapter 5. Our second lesson for Chapter 5 is Lesson 5.2 called Evaluating and Graphing Polynomial Functions. In Section 5.2, we're going to actually take a look at a couple different ways that we can evaluate a polynomial function for a specific value of x. We're also going to be talking about the graphs of those polynomial functions and what they look like. So in 5.2, we talked a little bit about what polynomials are, a little bit about how to combine them. We talked about some of the properties of power stuff. So we're going to shift gears and go back to kind of what we were talking about in Chapter 4, which is primarily looking at graphs of functions. Now we're looking at other functions like third degree and fourth degree and fifth degree, et cetera, et cetera. So we'll get to a little bit of that kind of stuff. But let's run through some vocab first. First of all, a polynomial. A polynomial is the sum is either a monomial or a sum of monomials. So if I have a series of monomials added together, for example, we can have something like, y equals x squared plus 2x minus 5. Okay, that happens to be a trinomial. It's second degree because the highest power of x is the second power. And so again, that's a polynomial because it has three monomial terms, x squared, 2x, and negative 5. A polynomial function is a function of the form f of x equals, and again, really this just says a sub n, so that's coefficient n, and then x to the n power. Again, x to the n power, so if it's nth degree, for example, suppose it was the third degree. All right, so this would be coefficient number 3, and then this would be coefficient number 3 minus 1, or coefficient 2, and then x to the second power. Et cetera, all the way down to a to the 1 x and then a to the 0. Now, so basically a's are your coefficients. All right, and in last chapter we called them a, b, and c because we knew for all the quadratic stuff we would have no more than a trinomial, so we could quantify them by having three coefficients a, b, and c. Now we're going to call them a sub n minus 1, a sub n minus 2, all the way down to a sub 0. All right. The exponents of all of these have to be whole numbers, okay? And the coefficients are also real numbers. Not necessarily whole numbers, but they have to be at least real number. You can't have coefficients that are imaginary, which we talked about in the last chapter. All right. Synthetic substitution is an alternate method to evaluate a polynomial function using fewer operations than direct substitution. Direct substitution says, for example, if I had f of x equals 3x squared minus 4x plus 7, and I asked you to find f of 5. That would say that you're going to do 3 times 5 squared minus 4 times 5 plus 7. Again, you're going to plug that 5 in every place you see an x, and then go from there. There's a better method, a shorter method, called synthetic substitution, which we'll be showing you during this section. All right? Now, end behavior is how a function behaves at its ends. So it says the behavior of polynomial functions graph as x approaches either positive infinity or negative infinity. So as we get into this a little bit, you'll have some sort of a function, and again, I'll just kind of draw some random function in here, and I'll talk more about what that is a little bit later on. But we're saying what happens to the function values as x approaches infinity, and what happens to f of x down here as x goes to negative infinity. And so by the way, that little symbol there means infinity. And so we're going to talk a little bit about that as well. So what happens to the function as x goes to infinity? What happens to x, or the function as x goes to negative infinity? So that's called end behavior. Basically, how does the function behave on its ends? All right. Functions have lots of different humps and shapes and things that they do in the middle. But the big thing is what do they do in the ends? And that's kind of primarily what we'd be focused on in this section. Okay? All right, so the first part is, it says identify polynomial functions. It says decide whether the function is a polynomial function. If so, write it in standard form and state its degree, type, and leading coefficient. All right, so in the first example, we look at this here, and it is third degree, but however, because this is not an integer, we would say that this is not as a polynomial function, because as we said all the powers have to be whole numbers. And in this case, since that's 2.5, that's obviously not a whole number. Since the term 4x to the 2.5 power has an exponent that is not a whole number. So that's not a polynomial. The second example, however, this one is a polynomial function. Now, it's not in standard form. Standard form says basically put the highest power of x and decrease from largest to smallest. All right, and so rewritten, this is f of x is equal to 9x to the 4th plus 3.7x and then, I'm sorry, let's start that one over again. It is a function. We were right there. This is then 9x to the 4th, so we're going to put that first, and then we're going to put our x squared, and then we're going to put our 3.7x on the end. Because again, highest power of x is 4, then 2, then 1. So we want to work largest to smallest. Now, just a little tip here, and you're looking at that and saying, well, that's not a whole number. Remember, the coefficients don't have to be whole numbers, just the powers do. All right? So then the degree is 4. All right? It has a degree of 4 because the highest power of x is 4. If the highest power of x was 5, it'd be a 5th degree. If it was 6, it would be 6th degree. Now, we have special names for those that are 2nd degree, right? So if the highest power of x is 2nd degree, like for example, x squared plus 4x minus 7, we called that a quadratic last chapter. Okay, so we already have a name for 2nd degree. For 3rd degree, we call that a cubic. Aptly named because 3rd power is cubed, so we call that a cubic. Now, they do also call a 4th degree a quartic. You know what? I will never call it that, all right? Because for me, 4th degree seems to be much easier to say than quartic. 5th degree, obviously, we could have special names for that, but pretty much anything past 3rd degree, which is cubic, we're going to call it 4th degree, 5th degree, 6th degree, etc. Leading coefficient in this case is 9 because, again, originally the leading coefficient was 1. When you put it in standard form, the leading coefficient is the coefficient of the highest power of x. Okay? All right, so we're going to go ahead and try a checkpoint problem. Try this one real quick. We'll be right back with solutions. It shouldn't take long. All right, so the solution for this one then, we want to put it in order from highest to smallest. First of all, is it a polynomial? Well, absolutely it is a polynomial because all the powers of x are integer values. So we want to go highest power of x first, and that happens to be at x to the 4th. Make sure you bring the negative sign with it because it's negative 3x to the 4th, so that whole term is negative. Negative 3x to the 4th, go ahead and cross that off, then minus 2x to the 3rd, and then plus 2x squared, and then plus 5. Now that we've got it in standard form, state the degree. Well, it's 4th degree. All right, the type, again, you can call it quartic if you want. I will never, so I'm just going to cross it off. And then leading coefficient, in this case, we'll just call it LC, is equal to negative 3. Make sure it's negative 3 because, again, that has to go with the x to the 4th power. All right, so I want to talk a little bit about this idea of synthetic substitution. Synthetic substitution, as we said before, is another way that you can evaluate, instead of doing a direct substitution. For example, in this case, they want to know what is f of 2. Now, the old way, we would have done 2 times 2 to the 4th power plus 3 times 2 to the 3rd minus 6 times 2 squared plus 3. You can see that this gets a little cumbersome, and the more terms we have for our polynomial here, the more cumbersome it gets. So what we're going to do then is we're going to take this, if we want to use what we call synthetic substitution, the first thing we're going to do is we're going to write the coefficients of f of x in order of descending power. Okay, so if it's not in standard form, this one happens to be because it goes 4th, 3rd, 2nd, and then there are no x to the 1st. And so it does go highest to lowest. All right, so we're going to write them in descending order. Write the value of x to the left. So the value of x that we want in this case is 2. And then the process says simply bring down the leading coefficient. All right. Multiply the leading coefficient by the x value that we're interested in. In this case, it's 2. And write the product under the second coefficient and then add. So the process says bring this down, which is in this case a 2, and then do 2 times 2 and you get 4. And then add again. 3 times 4 is 7. I'm sorry. 3 plus 4 is 7. And then 2 times 7 is 14. So when you are bringing this number to here, we're multiplying, but then over here, we're just going to be adding. All right. Now, you might wonder where this 0 came from. Notice that this was 2x to the 4th, 3x to the 3rd, negative 6x squared. There weren't any x to the 1st powers. But we can't leave that blank. We've got to put a 0 in there as a placeholder. All right. And so just as we're filling the rest of this out, again, we're going to bring that down and we're going to then add. We're going to multiply the previous sum by 2 and then repeat again over and over and over again. So again, these numbers are my coefficients. The 2 was from here, the 3 was from here, the negative 6 was from here, the 0 was the fact that there were no x to the 1st powers, so we have to have a 0 there. And then the 3 is the only constant on the end. So as we're working through this, again, I'm kind of all over the place here, but I just wanted to make sure you understood where everything came from. Again, bring down the 2. 2 times 2 is 4. 3 plus 4 is 7. 2 times 4 is 14. Negative 6 and 14 becomes positive 8. 2 times 8 is 16. 0 plus 16 is 16. And then 2 times 16 is 32. And then 3 plus 32 is 35. So what we're going to say then is we're going to say f of 2 is 35. All right? So you could go through this process. You could plug all this into your calculator, and you could get a value. But you can save some time by doing what we call a synthetic substitution. And trust me, you guys are going to say, well, I'm just going to stick with the old way. But this is going to serve a purpose in section 5.8. We're going to talk about what we could also do with synthetic substitution. And it's called synthetic division. And again, we'll explain that more in lesson 5.8. But this is a process that you need to understand because it is very, very important to what we're going to be doing later on. All right. The last piece of this lesson then talks about this idea of end behavior and how does a function behave on its ends. To teach this, I would probably start with a picture. And I'm going to say, look, if a is bigger than 0, if the leading coefficient here, and I guess they're going to call it a sub n, if the leading coefficient is positive, meaning greater than 0, all right, there are two things that could happen here. If a is greater than 0, then either you have an odd degree, meaning this is an odd number, or you have an even degree, or like this is an even number. So if, we're going to say n is odd or n is even. So an even degree polynomial, let's think about, go back to the last chapter. If n is even, say 2 for example, that's second degree, that's a quadratic, that's going to be a parabola shape. And as long as the leading coefficient is positive, we know that's going to open up. The way that I think about even degree, now we could go to ideas like 4th degree, 6th degree, 8th degree, 10th degree, etc. All right. If the the degree of the polynomial is even, then it's always going to finish where it started from. Wherever it came from, that's where it's going to end up. And since the leading coefficient is positive, that means it's going to come up. So you might get something that looks, something like that. Now again, that could be any of those degrees. It's certainly not second degree because we know second degree are quadratics, so it would be more of a parabola shape. But if n is even, meaning it's even degree polynomial, and the leading coefficient is positive, it's going to open up. All right, and again, it might do some other kind of weird stuff in between. It might be more shaped like this, more like a parabola. It might kind of go through and come back up and go back here. Either way, it's always going to end where it started. So if it starts from up here, it's going to finish up here. All right, so again, leading coefficient is positive, opens up. If it's even, it ends where it starts. Now, if the leading coefficient is positive and is odd, it's going to be something more along this lines. All right, it's going to start from down here, and it's going to end up here. All right, so we'll kind of look at some of these and fill in some of these blanks here in just a second. But odd degree, like again, for example, first degree, that's linear. Okay, if leading coefficient is positive, so for example, y equals 3x plus 1. Leading coefficient is positive, that's even, or that's odd, right? X to the first power. So that would be a linear function with a positive slope. If we get third degree, then you get something more like this, a cubic shape. If you get fifth degree, then it might be something more like this. It might be a little higher and kind of have a bump in it like that. It could come all the way down and back through, but it's always going to start down here and finish up here, so long as the leading coefficient is positive and it's odd polynomial. So odd polynomials don't finish where they start. They always finish opposite where they came from. So we started down here and we finish up here. All right, so that's the first case. What if that leading coefficient is negative? Well, let's do the one we're familiar with first. Let's first talk about even. Okay, if we're talking about n being an even power, meaning the degree of the polynomial is an even polynomial, and the leading coefficient is negative, that means it's going to open down. So it's going to look something like that. All right. Again, it could be a quadratic where it's more shaped like this. It could be a 4th degree and actually come down, back through, and come up again. But again, because it's an even degree polynomial, it always finishes and starts from the same area. Just like these ones, started here and finished up here. All right, so what do you suppose that n is odd is going to look like if the leading coefficient is now less than 0 or negative? Well, because here we started from down and went to finish up. Now we're going to start from up and finish down. All right, and so again, if the leading coefficient is negative, it's going to start up and it's going to finish down here. Now again, comparatively speaking, if the leading coefficient is positive, again, it's going to finish at positive infinity in both cases. If the leading coefficient's negative, in this case, it's going to finish down here at negative infinity. So that kind of tells you the end behavior. So let's fill in some of this stuff. Again, this is kind of more memorization. Guys, I really would rather you kind of think about, I want visual thinkers, all right? I want you to be a visual thinker. I want you to imagine when you get some quadratic or some parabolic function or whatever, some polynomial function, to start thinking immediately about what is this thing going to look like. So let's fill in some boxes here. It says if a sub n is greater than 0, meaning leading coefficient is positive and n is odd. Okay, leading coefficient is positive and n is odd. That's this guy over here. Then f of x approaches negative infinity as x approaches negative infinity. So as x goes further to the left, the values of f of x go further down. So as x goes to negative infinity, f of x goes to negative infinity. As f of x goes to positive infinity, as x goes to positive infinity. Again, as x increases, the values of y go way up here. All right, now let's continue with our odd. Okay, odd degree, again, now we're going to go over to here. Odd degree and the leading coefficient is now negative. F of x goes to positive infinity as x goes to negative infinity. The further left we go, the further up we go. So we go to positive infinity as x goes left. As x goes right to positive infinity, the values of f of x get down here, and so this becomes negative infinity. All right? So now let's look at those two that are, if n is even, now we're looking at even degree, and leading coefficient is positive. That's this one right here. Okay, it's going to start up and it's going to end up. So as x goes to negative infinity, f of x goes to positive infinity. Again, the further left we go, the higher we go. The further right we go, the higher we go. So in both of these cases, we're looking at positive infinity as x goes to either negative or positive. The end behaviors are both going to start up and finish up. And if a is less than 0 and n is even, then f of x goes to negative infinity as x goes to negative infinity, and it also goes to negative infinity as x goes to positive infinity. Again, that's this one right here. As x goes further left, the values of f of x are further down. As x goes further right, f of x goes further down. Now again, this is kind of a hard deal to come up with, and it's kind of a little bit challenging, but we want to be a visual thinker here. Before I even start with the solution, I want to imagine what this thing is going to look like. The leading coefficient's negative, and it's odd degree. Since it's odd degree, I know it's not going to finish where it came from, and since the leading coefficient's negative, that means it's going to finish down here. So I'm going to get something along this line. I have no idea if this is the right shape or not, but I know that as x goes to negative infinity, f of x is going to go to positive infinity. And as x goes to positive infinity, f of x is going to go to negative infinity. So I know it's going to be this kind of a shape. All right? So now we've kind of got an idea in our head. This is that whole visual thinking here. So I want you to first be this kind of a thinker. Be a visual thinker. Think about this picture before we even start with making a table. All right? So we've got an idea of what this thing is going to look like. So then we're going to go ahead and we're going to take a look at our graph. And I've already preloaded this graph into my graphing calculator. So if I turn this on and I go to y equals, our first function here, I've got the checkpoint problem in here already, by the way. Our first expression that we have in here, this first equation is this polynomial function f of x that we're looking at there. So we're going to go ahead and type that into our graphing calculator. Again, the -1 is going to bleed onto the second line. That's okay. Take a moment and do that. And if you need to pause the video to take the time to type that in, please do so. And then let's go ahead and let's take a picture and look at this graph. All right, so there's a graph of that function. Now, as we said, going back to our pen mode here, as we said, this thing is going to look something like this. You guys should have that sketched in your book already. Does that kind of match what we start with here? Absolutely. So now we need to pick values of x that are actually relevant. So to do that, we're going to use the trace feature on our graphing calculator, and we're going to kind of trace over here to the left. Now you'll notice that the end behavior says as x goes to infinity or negative infinity, the values of f of x are going to go to positive infinity. So you can see that that's kind of the end of our function. So we know we're seeing enough of it. We don't need to expand our window. We're seeing pretty much all we need to see. So in this case, x is negative 1.7, and we're way up here at 6. And so that says we're going to probably want to do a window somewhere around these values, like -2, -1, 0, 1, 2, 3. And then on the other side of that, let's go to the other end of our picture. And right around here, when x is like 3, y is -0.6 something. So, and it's only going to go down from there, because that's the right end behavior, right? We've got a picture of the right end behavior. So basically, we want to go from about -3 to +3. All right? So let's run over here, and let's fill in our graph. As they did here in the book, they picked these values of x for you. And so we're going to go to our table. And in our table, we're going to start at -3. And all we do then is we've already put the function in. When x is -3, y is 38. We're going to have a hard time graphing that point. When x is -2, y is 11. When x is -1, y is 0. -1, 2, 3, and 4. Oops, -4. All right, so we've got our points there. We can't graph -3, +38. We really can't graph -2, +11. But we can graph -1, 0. We can graph 0, -1. 1, +2, 2, +3, and then 3, -4. All right, now you're looking at those points and saying, man, how am I supposed to make a graph of that? Well, once again, go back over to your graph and take a look at what that picture is supposed to look like. We know what our end behavior is. We know it's going to finish down here, and we know that it came from up here somewhere. So now we just kind of have to make a smooth curve and connect those dots. Now we've got a pretty good idea of what that thing looks like. All right. We've already addressed all this. Obviously, the degree is odd. The leading coefficient is less than 0 or negative. So as f of x goes to positive infinity, as x goes to negative infinity. So as we go further left, f of x goes way up here. As we go further to the right, f of x goes further down. So as x goes to positive infinity, f of x goes to negative infinity. All right, so you have 2 checkpoint problems. Please pause your video, and I want you to try the 2 checkpoint problems at the bottom of the page, please. All right. So if you left your video running, I've already put in for the function already for f of x here. So if you paused it, then you may not have seen that. But first thing we want to do is we want to evaluate f of x for -2 using synthetic substitution. Now the old way with direct substitution would tell you to make this negative of -2 to the 4th plus 3 times -4 to the 3rd. I'm sorry, -2. -2 to the 3rd. Plus -2 squared minus 4 times -2 plus, that's a lot of work, right? And there's a lot of places we can screw up with a sign. So instead of doing that, we're going to use our idea of synthetic substitution. I'm going to draw my bracket here, and I'm going to put in the coefficients of my terms: -1, +3, +1, -4, and -1. Now again, I didn't have to put any 0 placeholders in here because I had 4th, 3rd, 2nd, 1st, and then no x's on the end. So I want to substitute in -2. Bring down this becomes -1. Now multiply, negative times a negative is positive, so this becomes +2, and then add, this is 5. -2 times 5 is -10, and now we add, 1 plus -10 becomes -9. And then -2 times -9 becomes +18. When I do -4 plus 18, I get 14. And then -2 times 14 becomes -28. -1 plus -28 becomes -29. So f of -2 is equal to -29, and that saves me the trouble of doing all of this. I'm going to use synthetic substitution instead. Now it wants us to make a graph of this. Now, since it's even degree, that means that it's going to be like this, or it's going to be like this. Okay, the question is which one is it? Well, it's obviously this one. And why do I know it's this one? Because the leading coefficient here is -1. So that means that it's going to start down and end down. So as x approaches negative infinity, f of x will also approach negative infinity. As x goes to positive infinity, f of x is going to go to negative infinity. So the further left we go, the further down we go. The further right we go, the further down we go. All right, they're both going to move off to negative infinity. So that means my graph's going to be down here and then finish down here. All right, the question is what are some points in between? So what we need to do then is we need to go back to our calculator, and we need to get a picture of what this looks like to pick valuable numbers for x, for our little table here. All right, so we plug that function in, and I'm going to go ahead and I'm going to graph it. Here's a picture of that function. All right, and as promised, we can see enough of it to recognize the fact that this thing starts down here and it finishes down here. It's going to do some funky things in between, but it's going to start down and finish down because the leading coefficient is negative and it's even degree. All right, so now we just got to pick some points in between. So again, as I told you before, I use my trace feature to say what are valuable numbers for x to even plug in here. I don't want to put numbers in like negative 10 because that wouldn't make any sense. Pretty much this thing runs off to infinity as x is like negative 1 or negative 2. All right, and then the further we go here, as we go over here to the right, we get to our maximum, which we'll call a local match. We'll talk about that a little bit later on. And it looks like I should probably pick values of x till we get to somewhere around 2 or 3. All right, so I want to go from x and y. I want to pick numbers like negative 1, 0, 1, 2, and 3. And that should give me a pretty good picture. Now, once I have that idea, then I'm going to use my table feature. Go back over here to second table. And in my table feature, again, as promised, as x is negative 3, y is negative 166. We don't really care for that number in our table at all because that's not going to help us much. All right? But looking at these other numbers, like in here, when x is negative 1, y is negative 8. When x is 0, y is negative 4. When x is 1, y is negative 2. When x is 2, y is 4. And when x is 3, y is negative 4. And so let's plot those points. Negative 1, negative 8 is way down off the page. We can't see that one. But 0, negative 4, 1, 2, 3, 4 is right in there. 1, negative 2 is right in there. And let's see, 2, 4 is over 2, 1, 2, 3, 4. And then 3, negative 4 is 1, 2, 3, 4 right in there. All right, so now what we have to do is we kind of have to make a smooth curve so we know it's going to come from down here somewhere. Remember, negative 1, negative 8 is like way down here somewhere in the middle of my chart. So it's going to kind of come up, bend, come up to the top, and then go back down to the bottom, something like that. All right, and so that's kind of how we use end behavior to pick what values of x that we even want to try to make a graph of something like a 4th degree polynomial.